The question is, could you tell us how to represent 3D state of strain? Let's start by recalling the simplified definitions of strain. First, we define the normal strain, and in doing so, we considered a one-dimensional rod subjected to a tension P, like shown in this picture. The normal strain, epsilon, was defined as delta over L naught, where delta is the displacement or change in length. L naught is the original length. When we use the original length L naught in the definition, this is also called the engineering normal strain. Otherwise, it would be called the true strain. The shear strain, gamma, was, on the other hand, defined as the total change in the angle between two lines that are perpendicular to each other originally, expressed in radians, right? Say we take two lines OA and OB that are initially perpendicular to each other. Say OA deforms into OA prime and OB deforms into OB prime. Then the shear strain gamma would be the change in angle, which is pi over 2 minus theta, which would be simply gamma 1 plus gamma 2, where gamma 1 is this angle and gamma 2 is this angle. The gamma defined this way is called the engineering shear strain. There's also another one called tensorial shear strain, which is half the engineering shear strain. So with respect to two perpendicular axes, axis 1 and axis 2, epsilon 1 to the tensorial shear strain would be gamma 1 to the engineering shear strain divided by 2. We kind of mentioned this, but we didn't elaborate on this earlier, right? But this is going to be the starting point for the discussion in this video. Remember a picture similar to this I used in the discussion on stresses, right? Basically, we have a three-dimensional body subjected to some external forces like these and supported at certain points like these, right? If I section the body along a plane like this, we said the state of stress in general vary from point to point. In other words, the state of stress at point 1 is not going to be the same as state of stress at point 2, which is not going to be the same as the state of stress at point 3, and so on, right? Well, this is true for strains as well. Strains do vary from point to point in general. Just as stresses are three-dimensional, strains are three-dimensional as well. Remember we said stress is a quantity called tensor, T-E-N-S-O-R, right? Usually we use a matrix notation to represent the components of a stress tensor. In general, you need 9 components to represent a state of stress, but it can be shown that this matrix is symmetric about the diagonal, right? And therefore, there are only 6 independent components. And here is the corresponding strain matrix. A couple of things to note here. Firstly, epsilon xy and so on, the off-diagonal terms, are what we refer to as the tensorial shear strains. Each component of the tensorial shear strain is half the corresponding engineering shear strain, gammas. So epsilon xy is gamma xy over 2, and similarly epsilon xz would be gamma xz over 2, and so on. Secondly, just as the stress tensor is a symmetric tensor, this strain tensor is also symmetric, and therefore epsilon xy would be equal to epsilon yx, and so on. And therefore you only have 6 independent components that are needed to represent the state of strain at a certain point in a three-dimensional solid. Out of the 6 independent components, 3 of them are normal strains, which are epsilon xx, epsilon yy, and epsilon zz. These are normal strain. And then epsilon xy, epsilon yz, and epsilon xz are shear strains. Let me illustrate the physical meaning of the strain components with respect to a two-dimensional state of strain. We have a rectangular body ABCD which deforms into A prime, B prime, C prime, D prime, with their opposite sides being parallel to each other. In other words, A prime, B prime is parallel to C prime, D prime, and A prime, D prime is parallel to B prime, C prime. Say this distance over here is dux and this distance is duy. and the original length in the x direction is dx, original length in the y direction is dy. Furthermore, note that if this is dux, this is dux, and if this is duy, this is duy. Also, we note that for this 2D state of strain, the 3 by 3 strain matrix simplifies to 2 by 2, like shown here. The two normal strain components are epsilon xx and epsilon yy, and there's only one shear component, epsilon xy, which is equal to epsilon yx, which is also equal to gamma xy over 2. So let's look at the physical meaning of the normal strains first. Epsilon xx is the change in length of the body in the x direction divided by the initial length of the body in the x direction. So if I consider this line AD, right, that deforms into A prime, D prime, where A prime coincides with A, but D prime is different from D, right? The change in length in the x direction would be dux, initial length is dx, and therefore epsilon xx would be dux divided by dx. And similarly, epsilon yy would be duy divided by dy. Now let's talk about the physical meaning of the shear strain. You may recall that for small angles, tan theta and theta are very close to each other. Assuming that dux is very small compared to dx, then tan theta 1 would be duy divided by dx. Theta 1 in turn would be equal to tan theta 1, which is equal to duy divided by dx. Similarly, looking at this triangle, theta 2 equal tan theta 2, which is equal to dux over dy. The shear strain gamma xy is by definition equal to theta 1 plus theta 2, right? So a total change in the angle. That will be dux over dy plus duy over dx. Epsilon xy, of course, is half of that. So it will be half time dux over dy plus duy over dx. Now you have a physical meaning for the components of the strain tensor. Going from 2D to 3D is straightforward but complicated to visualize. Let me also briefly introduce what is known as the tensorial notation. Just for reference, let me just leave the system we've been using so far on the left here. We've been using the XYZ Cartesian coordinate system where the strain tensor is given by this matrix right here, right? The components here are epsilon xx, epsilon yy, and so on. Another convenient notation called the tensorial notation for the strain is this. Here, instead of calling the three axes as xyz, we call them as x1, x2, and x3. Instead of calling the deformation as ux, uy, uz, we call them here as u1, u2, and u3. Then this single tensorial expression for the strain tensor will generate all 9 components you see in this matrix. I here goes from 1 through 3 and j goes from 1 through 3. You pick a particular value for I and a particular value for j, and this equation will generate the corresponding strain component. For example, if I is 1, j is 1, you come in here and you substitute 1 for I and 1 for j, right? So you have epsilon 1, 1 on the left side. On the right side, we have half time du1 over dx1 plus du1 over dx1 again. So that kind of simplifies to du1 over dx1. And similarly, if I pick I equals 1, j equals 2, we get epsilon 1, 2 on the left side. On the right side, we have half time du1 over dx2 plus du2 over dx1. Now let's talk about sign convention. The sign convention for the normal strains are pretty straightforward. If you have tensile strain, they are positive. If you have compressive strains, they are negative. The signs of shear strains can be, however, complicated. Let's consider a 2D state of strain with respect to xy directions with deformation du, delta u, and delta v. Here I'm considering 4 different cases with respect to the xy coordinate system. We want to consider the deformation of 2 perpendicular lines which are drawn in blue in each of these 4 pictures. Each picture represents a particular case. So let's call this a case 1, this is case 2, this is case 3, and case 4. In case 1, line in the x direction is in the positive x direction. Line in the y direction is in the positive y direction. And these directions keep changing in each of these cases. So for example, in case 2, line in the x direction is in the negative x direction, line in the y direction is also in the negative y direction, and so on. In each of these cases, the two blue lines deform into two red lines. Let's consider one of these in detail. Let's consider case 1 in detail. The angle between the two red lines is smaller than the angle between the two blue lines like shown here. If I call the deformation here as delta V, you can see delta V is greater than 0 because it's in the positive y direction. If I call this deformation as delta U, once again you can see delta U is greater than 0 because that's in the positive x direction. And this distance is delta x and that distance is delta y, both of which are once again greater than 0 because they are all in the positive x and y directions respectively. By definition, gamma xy, the engineering shear strain, is given by this equation. The first derivative here can be approximated as delta u over delta y. Since each of these terms are positive terms, you can see this angle right here, theta 1, is greater than 0, right? The second derivative here is approximated as delta v over delta x, which again is greater than 0. And therefore, gamma xy is greater than 0. And therefore, the initial angle of 90 degrees decreases during deformation. Then the shear strain is greater than 0 for this case. Now you get the idea, right? So you can follow these cases yourself. So in the second case, if the angle decreases, the shear strain is 0. In the third case, angle must increase like this for the shear strain to be greater than 0. And in the fourth case, the angle must increase again for the shear strain to be greater than 0. Here's the summary of our findings so far. For cases 1 and 2, the angle must decrease for the shear strain to be positive. For cases 3 and 4, the angle must increase for the shear strain to be positive. Here are some further facts about strain. The first one, we already mentioned that there are 6 independent components of the strain tensor in general. However, depending on the problem, one or more of the 6 components can be 0. So this is how we come up with the 1D and 2D problem for generally a 3-dimensional problem. Finally, just as in the case of stress, the strain components with respect to XYZ system are different from those with respect to a rotated coordinate system x prime, y prime, z prime. Here's a further illustration of that for a 2D state of strain. The components of the strain in the rotated coordinate system x prime, y prime can be found as a function of the components of the strain in the original xy system and the angle of rotation theta. The corresponding law is called the transformation law.